Hi, welcome to our study of scatter plots and line of best fit. So we're going to start with a survey that was given to students in the Freshman Academy after the first week of the semester. We asked how many pairs of shoes they owned and how many tardies they had. As you can see, we created a table here, and then we created a scatter plot. The x-axis is the number of pairs of shoes, the y-axis is the number of tardies. Now when we look at this, we can see a general positive shape of the point, so we're going to draw our line of best fit. Here's the line of best fit that I drew. It should follow the trend of the data and have approximately the same number of points on both sides of the line. Once you have your line drawn, we're going to estimate what the slope and the y-intercept are. So if I choose 2 points on this line, I can see that I go up approximately 2 up and 2 to the right, which is a slope of 2 over 2, which can be simplified to 1. So our slope is approximately 1. We're going to do the same thing and just estimate where's our y-intercept. It looks like it's right here between 2 and 3, so I'm going to call that 2.5. Now, again, we're just approximating our line of best fit, so we're just going by what it looks like. In a moment, we'll use technology to see what the exact one is. So we're going to write our equation, which is y equals the slope, 1, x plus our y-intercept, which is 2.5. Now, if you notice, our y has an extra little mark on it. This is called y hat. We're going to use that when we use the line of best fit or the predicted equation because it's not an exact fit. So our line of best fit that we got was y hat equals 1x plus 2.5. Let's see how close we were. Using technology, we got y hat equals 1.03x plus 2.49. This is pretty close. We also can see that r here is 0.531. I'll explain in just a few minutes what that is. The next thing that we need to do is we need to interpret what each part of the equation means in context. Well, if you remember, slope is rise over rise. So our slope is 1 over 1. Now, if you think about the context, that's going to mean 1 tardy for every 1 pair of shoes. Because remember, slope is rise over run, so our rise is number of tardies, our run is number of pairs of shoes. So it means that it's going to increase 1 tardy for every 1 pair of shoes. Now, whether or not that makes sense, we're going to look at in a little bit. Now, remember, our y-intercept was 2.5. So that means that there are 2.5 tardies when you have 0 pairs of shoes. All right, so why do we even use a line of best fit? It's so that we can predict values in the future or on the scatter plot that we haven't collected. So according to the model, if you have 20 pairs of shoes, how many tardies do you have? So the first thing that you need to decide is if 20 is your x or y. Well, I can look on my scatter plot and see that pairs of shoes is going to be our x, so we're going to fill in 20 for the x. So we've got y hat equals 1.03. Now we're going to plug in our x here of 20 and then add our y-intercept, which is 2.49. After calculating, we're going to get the value or the predicted value of the y or the number of tardies. So when we do the calculations, we get y hat equals 23.09. Now, since we're talking about tardies here, I'm going to round that, so I can just say 23 tardies. So, in context, that means that if you have 20 pairs of shoes, you have 23 tardies according to our model. Now again, that may not make sense, but that is what our model would predict. Now, our next one says, according to the model, if you have 20 tardies, how many pairs of shoes you have. Now I can see that tardies is on the y-axis, so we're going to substitute that in for y. So I've got 20 equals 1.03. This time we don't know x, so we're going to leave it as x, plus 2.49. Now this is just a regular equation that we're going to work backwards to find. So we're going to subtract 2.49 from both sides, and then we will divide by 1.03. So after I did the math and the calculations, I got exactly 17, which is 17 pairs of shoes. So according to our model, if you have 20 tardies, you have 17 pairs of shoes. All right, now let's quickly talk about causation versus correlation. So correlation describes how strong the relationship is, which means how close the points are to the line of best fit. Causation implies that the independent variable, or x, causes y, or the dependent variable. So I always ask myself here, does x cause y? So let's look at our example. So does the number of pairs of shoes cause the number of tardies to increase? Well, no. So even though there's a strong correlation, we say there is no causation. Let's look at this next example. The amount of siblings you have and the amount of Instagram followers have. Do you have causation? Well, does the number of siblings you have cause the amount of Instagram followers? No. So there is no causation. What about here? X represents shoe size and Y represents what time you wake up on an average school day. Although these points closely resemble a line, obviously your shoe size does not determine what time you wake up. So no, there is no causation here. Let's look at one more example. Here we're talking about X represents the number of hours studied and Y represents your test grade. Does the number of hours you study have an effect on your test grade? Yes, so there would be causation here. Now let's talk about what this little number r means. R is known as the correlation coefficient. It labels how strong the relationship is or how close together they are on a scatter plot. R has to be between -1 and 1. All right, so let's talk about there's two groups here. If R is between 0 and 1, we're going to say that that has a positive correlation. Now, positive correlation also means it has a positive slope. And again, this is different than causation. On the left-hand side of the number line, from -1 to 0, this is a negative correlation, which means it has a negative slope. Now, we have all sorts of different strengths, okay? The closer it is to 1, the stronger the relationship is. So if the correlation coefficient is close to 1, it's going to have a strong correlation. As you can see on this scatter plot here, the dots are very close to the line. Similarly, if it's close to -1, it's going to have a strong negative correlation. As you can see on this scatter plot, they go in a negative direction, but they're also very close together. If it has a correlation of 0, it's going to be no correlation. Now, as you get closer to 0 but still positive, it's going to have a weak correlation. What's this going to look like on a scatter plot? It's still going to go up positively, but it's going to be spread out a little bit more. And the same thing is true over here for a weak negative correlation. It's going to be closer to 0, and it's going to be spread out but going in a negative direction. So what would no correlation look like? No correlation would be a scatter plot that is just all over the place with no correlation. So let's look back at our other examples and figure out what the correlation coefficient means. So on our mini lesson here, we have R equals 0.531. So the first thing I ask myself is, does it have a strong, positive, weak, or no correlation? So I can see here that it's positive, so it's going to have a positive correlation. But 0.531 isn't really close to 1 or 0, so I'm going to say relatively positive correlation. It's not strong, it's not weak, but it's moderate. All right, let's take a look at our next example, 0.872. That's definitely positive, and that's going to be strong. So we're going to say that that has a strong positive correlation. Now notice, even though it has a strong positive correlation, there's no causation, so you can have one without the other. 0.767 is also strong positive, and 0.959 is too. So what would it look like if it were going to be weak negative or weak positive? So if you have a correlation coefficient of, let's say, negative 0.93, that's going to be strong negative correlation. Again, the negative just lets us know that it has a negative slope, but it is very close to -1. What about r equals -0.32? It's still negative, but that's going to be a weak negative correlation. All right, I think that's it. That's a lot of information. Oh, but we have one more thing. Let's talk about residuals. So residuals lets us know if a line is even a good fit. So what we do is we use our line of best fit, which was y hat equals 1.03x plus 2.49. And we complete a table of values. So here's the number of shoes that we collected. Here's the number of tardies that we collected. And in this column right here, we plugged in the different x values to find out what the expected tardies would be. Then we took this first column, 2 minus 3.52, to get our residual, or how far our error was. We did the same thing here with 4 minus 3.52, and we did that all the way down. Now, if you add up all of those residuals, you're going to get a sum of 0. Now, the last step is to calculate or plot the residual plot. We're going to plot the x values and the residuals or the errors and see what we get. Here's what our residual plot looks like. We are actually looking for a random plot when we're looking for a good residual plot. As you can see, there's no real pattern here, so that means that there is a good fit. If you were to get something that had a general shape, something like this, on a residual plot would actually be bad. Or it could even go down like a U, and that would let us know that this is not a good fit. All right, please let us know if you have any questions. Feel free to review parts of the video and make sure that your notes are complete. Thanks.